Hi, it's Will. Welcome to my beginner's guide to the Aurora. Every photograph you've ever seen of the Aurora taken from the UK, from the USA, Australia, is not what the photographer saw. This is because the camera enhances the colours, and often photographers will saturate images to make it look even brighter. So to give you a better idea, this is what we actually saw. Not as colourful, not as bright, but not bad. But let's think about this for a moment. I was in Northumberland looking north. Let's imagine that actually I was 600 miles further north on this night. In reality, I would have been closer to the Aurora. And therefore, the colours would have been visible by eye, and it would have been almost above me. So the answer is actually, the closer you are to the Aurora, the brighter it appears. And to give you an idea what that's like, here's a photograph I took with my iPhone in Iceland, and this is pretty much what we could see with our own eyes. Absolutely incredible. So there's two things to consider. Number one, the Aurora appears differently depending on the strength of the display and your location. And the key is to be out at expansion phase when the Aurora really picks up. Now, don't get me wrong, I love the Northern Lights. I've seen it on the horizon as a faint little glow, and I will literally stay out for hours and hours and hours just watching it. But in my opinion, the true experience of the Aurora is when you can look directly above you and you can see the light swirling around, all of the colours visible by eye, the pillars going up hundreds of miles above you. It is truly incredible. To give you a taste of what that's like, here is real-time video that I took with my camera looking directly above. This gives you a real sense of what the Aurora actually looks like because it's real time, it's not long exposure, it hasn't been saturated. I've been lucky enough to see the Aurora hundreds of times, and I have to say every display is different. When it's above you, it can be moving really fast with beautiful colours. It can be moving at a slower pace, but this was a stunning display, just slowly moving and developing. Really, really amazing. So, depending on where you are, you do see the Aurora differently. One of the rarest types of Aurora that you can see is the coronal Aurora, the crown, when you're looking directly above, and it's just honestly incredible. It goes off to a vanishing point. This was an incredible display at sea, on deck. It's truly incredible with no light pollution. It feels like you could literally touch the Aurora. So on that note, if you're not aware, I am doing a full charter cruise to Norway. We're going to be chasing the Northern Lights. Check it out, guys. It'd be great to have you on board.
Hi, my name is Will. I'm an Aurora Chaser. I've seen the Northern Lights over 350 times, and I am so excited to share with you that I have privately chartered a cruise ship, Ambition with Ambassador Cruise Lines. We're heading off to Norway with some of the darkest skies and one of the best times in a decade to see the Aurora, coupled with a major meteor shower. Will have shooting stars and the Aurora at the same time. Using satellite data, I'll be able to inform everyone with advance notice when to get up on deck and to see the expansion phase when the Aurora really picks up in activity, in brightness. And I cannot wait for you to join me. Check us out at willscruises.com.
So it'd be great to have you join myself and team. Honestly, it's going to be the most incredible once-in-a-lifetime trip. I cannot wait. So So let's get into it. Why and how does the aurora occur? Well, it's no surprise. It all starts with the sun. The sun gives off energy, heat and light, but it also gives off something called plasma, the fourth state of matter. Charged particles firing off in all directions. We call this the solar wind. Eventually, it arrives at Earth, but luckily for us, Earth has an iron core. Its outer core is liquid, moving, which then generates a dynamo, which then creates a magnetic field. This is the natural shield that we have, deflecting the solar wind away. So as you can see from this animation, these charged particles actually travel pretty fast. On average, about 1 million miles an hour. However, sometimes the winds pick up, overwhelming the natural shield. Let's talk about the one you've all heard of, solar flares. Magnetic field lines leave the sun. Sometimes they loop back down again. Where it leaves the sun surface and re-enters, we have something called a sunspot. Now, this is quite important for later on. But if you look at this diagram, sometimes material actually travels along these magnetic field lines. Just to give you an idea of scale, have a look at this. I don't know if you can see, but that is Earth for scale. They're absolutely massive. You could actually fit over 1 million Earths inside the sun. Now here's something pretty cool. Because the sun is made out of gas, it has what we call differential rotation. Different parts of the sun spins at different rates. At the equator, it rotates once every 24 days. At the polar regions, once every 30 days. Now this is pretty cool. Remember those magnetic field lines that I showed you in the previous diagram? Well, let's imagine one part of that field line landed on a faster moving part of the sun. Over time, these field lines would get twisted and entangled. So you can see if the sun equally rotated at all points, the lines would loop up and loop back down again. But because the equatorial region spins faster, it starts to wind up. Now, here's the cool bit. When two field lines moving in the opposite directions touch, they give off an incredible burst of energy called a solar flare. Now, these solar flares have different categories of strength, and all you need to know is that X and M flares for aurora chasing are typically the ones we're most interested in. But here's the most important thing. With solar flares, it does not guarantee that there's aurora coming. What you need is an eruption. Okay, so let's use this animation to go through what I've just covered. The sun is giving off this energy we call the solar wind. Now, sometimes we have solar flares, magnetic field lines that touch. Big burst of energy. If we're lucky, an eruption can occur. Billions of tons of gas, spits of the sun itself, is fired off, travelling up to 5 million miles an hour. This time taking just 1 to 2 days to reach us. But because it is denser, faster moving material, now the solar wind passes the Earth, continuing its journey, but the night side of Earth, the magnetic field lines, they actually trap some of the solar wind. They then go through a process, magnetic reconnection, where the magnetic field lines of Earth touch. They then fire energy back into the polar regions. It's just how the magnet is constructed. Now, this is where the magic happens. These charged particles enter the atmosphere where they heat up the atoms, giving the atoms energy that they do not want. So these atoms, which we call are excited, they need to get back to their ground state, and the only way they can do that is to release light. That is the aurora. So here's the thing. If this huge cloud of gas is heading towards Earth, which can then generate aurora, we need to know about it. And in actual fact, it's not so much for us aurora chasers, it's for space agencies to know whether or not they need to take action to protect their satellites, because obviously They've spent a lot of money having different instruments up in space, even the International Space Station with astronauts on board. They need to be aware of any incoming dangers. Do not forget, this is harmful radiation. This is a really cool animation and I really wanted to share it with you. So this is real modeling on a recent Aurora display and the effect the elevated solar wind had on satellites, because there's actually been quite a few incidences where satellites have been destroyed from very powerful solar winds. There's even a belief actually that the Apollo astronauts were very lucky because they made their journey to the moon when the sun was at solar minimum and therefore solar radiation was fairly low. So it's very important, especially with more space travel planned, more satellites, for scientists to be able to monitor the solar wind and things they can do to protect their instruments and space travelers. Now, remember we talked about solar flares, and from flares we can sometimes have coronal mass ejections. So one of the clues to whether or not there's going to be a chance of aurora is looking at the disk of the sun. Now remember, you need proper equipment to be able to monitor it, but sunspots means the sun is active and there's a chance of solar flares. So the higher the number of sunspots, the higher the chance of solar flares, which then also means a chance of coronal mass ejection. Now, I'm sure you have heard about this already. There is a natural 11-year cycle of activity, where every 11 years we have what's known as solar maximum, where the sun fires off a lot more flares and therefore higher chance of coronal mass ejections. Right now in 2025, we are still in solar maximum, and that should continue for a few more years. Okay, so we talked about the most powerful way in how auroras can occur, these coronal mass ejections, CMEs. But there are also other ways in how we can have enhanced solar winds. Coronal holes. Now, coronal holes aren't actually holes in the sun. It's just the way that the magnetic field lines are structured on the sun. Instead of being closed and looping back down onto the surface, they just basically stay fired out, enabling solar particles to stream from the sun at a faster rate. Coronal holes are more common during solar minimum, and often they can actually be there for a few rotations. So once you have a big hole that's creating aurora, you could look at a cycle of every 27 days. But this isn't always effective. However, it can be useful for longer term forecasting. So we know that the sun rotates. Now, as it rotates, if you can imagine, it kind of pushes the solar winds in a circular motion. And you can see this with the Hux animations here. If you have a faster moving wind from the sun caused from these coronal holes, they push in to the ambient solar wind as they rotate. The point at where it does this, we have a bit of compression. As a result of this, when this compressed solar wind reaches Earth, it could then generate decent aurora. So like a lot of Aurora Chasers, we're not fans of the KP index. It's a very generalized idea that when the aurora is a certain level, then you can see it at lower latitudes. So you'll see it a lot. They'll say, oh, KP9 forecasted next month, for example. However, as you will see later on, the KP index is only really good for giving us a very rough idea of potentially how strong the aurora could be. For real-time aurora chasing, it is pretty much useless. Locations over North America are more likely to see the aurora at lower latitudes than over Europe. And this is because geomagnetic latitude is different to geographic. So this is why, if we're seeing the aurora, say, at 55 degrees north at Europe, it does not translate to 55 degrees in North America. They see it at lower latitudes. Very interesting. The closer you are to the aurora, the brighter it appears, but the further away you are from it, the fainter it looks, and that's when the use of a camera will bring the colours out So then really to see the aurora at its best, you need to get close to it. That's either by travelling further north towards the auroral oval, waiting for those amazing storms when it brings the oval further south towards you, and most importantly, experience the aurora when it's going through expansion phase. You can access these models which projects where you can potentially see the northern lights, but the important thing to see is the correlation between KP index. Now, as you can see, we're moving along towards the right, the aurora is getting stronger, so therefore you can see it at more southern latitudes. So the KP index isn't very reliable because it is based on the global average over the last 3 hours. It is using historical data. What the KP index is unable to do is to predict when these bursts or the expansion phase occurs in the aurora cycle. It is during those moments where you can see the aurora much further south than you would expect using the KP model. When it comes to aurora chasing, we have a secret weapon, satellites that are sat 1 million miles upstream. They receive the solar winds first. They then relay this information to us. We then analyze it and work out what's going to happen. Phases of the aurora. There are 3 main phases to be aware of: growth, expansion, and recovery. The growth phase is typically when you see an arc. This can last hours and you're just waiting and wondering if anything is going to happen. Expansion phase is when the aurora comes alive. It brightens up dramatically. It can move further south in latitude and it's just unbelievable. That is the time when you want to see it. Recovery is when the aurora starts to wane, it turns into a diffuse glow, and you wait for the cycle to continue and repeat itself. Okay, so just to give you an example, this was taken with my phone in Iceland, 11 minutes past 1. This is growth phase. You can see the arc. But just 30 minutes later, it just went crazy. This is expansion phase. You have to be patient. You have to wait for it. Here's another example. St. Mary's Lighthouse. We had a visible arc, but then moments later, expansion phase, the sky's just lit up. It really is about waiting for that crucial time. Traveling south from Norway, growth phase lasted hours, but then expansion came and it really was worth the wait. I want to share with you this time lapse of growth to expansion. Absolutely beautiful, taken in Iceland. So you can see the aurora does change dynamically, and it's all about being patient. So it really is all about the closer you are to the auroral oval, the brighter it appears. Now, why do we have different colours? Once the solar winds travel into the atmosphere, they directly heat up the atoms. Oxygen, nitrogen, hydrogen atoms. They get excited, they receive this energy, and they turn it and release it as photons. That is the aurora. Depending on the altitude and density of the atoms, you see different colours. Reds are high altitude oxygen atoms and the greens are low altitude oxygen atoms. So there are loads of Aurora apps out there. I'm actually working on one which I'll be launching soon. But Aurora Now, My Aurora Pro, Space Weather Live are the main ones that I use. When you're looking at these apps, it typically gives you 4 main metrics: speed of the solar wind, the polarity, the strength, and the density. The one that I focus on is the polarity of the solar wind. The more negative it is, the stronger the aurora could be. And that for me is the most important thing. Now, I could do a whole talk about using the apps and the data, and I will at a later stage. But for now, when you have these apps, there is an option to look at something called hemispheric power. Some Aurora Chasers use it, but it's a calculation based on the different metrics that then comes up with a number. And for Aurora Chasing, I typically want that to be as high as possible, at least a 50. As it gets into the hundreds, then it's pretty exciting. Now, the different metrics all mean different things. The speed of the wind, for example, typically means the further south you can see it. The density typically means the more vibrant the aurora is. But for just beginners, I would suggest the hemispheric power is a very useful tool. Looking at the different apps, it gives you access to these four main metrics. You can see the trend lines. And the great thing is you are looking forwards in time. So by seeing what's going on, you can give a prediction of what's going to happen. Now remember the 27 days coronal holes. The long-term forecasting you find on these apps and tools and websites is based on these coronal holes. But remember, the further ahead in future you go with these forecasting, the less accurate it is. But it is pretty helpful for you to work out what are the chances. Other things that's really cool is analyzing the sunspots. Remember, the spottier the sun, the higher the chance of solar flares. There are instruments that monitor the side of the sun we can't see, so you can forecast in advance chances of solar flares. But again, it is simply guesswork. So when is the best time to chase the northern lights? You'll often hear the northern lights season is between September to April, and then April to September for the southern lights. Well, actually, there is data to suggest that March and September, October and April are the best months to chase the northern lights. And this is because of the equinoxes. Statistically speaking, when Earth is tilted up and down during the equinoxes, the solar winds better connect with the magnetic field, therefore higher the chances of aurora storms. This does not mean that if you go in December, January to Norway, Iceland, you'll not see aurora. It just specifically talks about these big solar storms where you see the aurora further south in latitude. What about the time of the night? Depends where you are on Earth witnessing it. Now, I'm sure you've heard of the North Pole, but we also have a magnetic pole and geomagnetic pole. And this is based on the magnetic field within Earth's core. The best time to see the aurora is at magnetic midnight, depending on your location. This is because the auroral oval is stretched further south when it's opposite the sun. So, places like Norway or Iceland, their magnetic midnight is slightly earlier, about 9 p.m. to 10:30 p.m. The Bortle scale is super helpful. Every location in the world has a rating of how dark it is. A 1 is the best place to stargaze, a 9 is the worst. So I recommend using lightpollutionmap.info. You can really zoom into locations and make sure you're in the dark sky. But more importantly, with northern lights chasing, you need to think about what is north of your location. For example, if you're heading off somewhere that's nice and dark, but north of you there's a major town or village, that will really hinder your opportunities to see the aurora. And of course, the opposite for the southern hemisphere, making sure nothing is south of you that's going to create that light pollution. Thinking about the moon phase is really important. If you go off stargazing, chasing the aurora when there's a very bright moon, it will impact how you see the aurora and how you photograph it. Here's some examples. Full moon with aurora in Northumberland, and then no moon with aurora in Northumberland. What a difference it makes. The higher up in latitude you go, the less of an impact the moon has. With the moon in Iceland, you can see what it looks like, and without a moon, nice and vibrant. Now, sometimes if you have a bit of a moon in the sky, it can light up the landscape for you and you can take some lovely photographs. So that's something to consider as well. So the best thing to do is to plan when there is no bright moon in the sky or the moon hasn't risen yet. Using time and date, I just double check to make sure wherever I'm going to, the moon isn't going to hinder my photos. And remember, even at quarter moon, it might have already set before you start to chase the aurora. Using timeanddate.com, you can look at how quickly the sun goes below the horizon, because with chasing the northern lights, you have to wait till the end of astronomical twilight, when the skies are nice and dark. Of course, when it is really strong, you can still see it at twilight, but you're talking about very strong events. And then also, with time and date again, you can type in a specific location and it'll tell you the exact minutes to get ready and set up. So I use these websites all the time. Okay, so a quick recap of best chances to see the aurora. Find places with low light pollution, choose dates closest to the equinoxes, make sure there's not a bright moon in the night sky, find magnetic midnight based on your location, look out for these coronal holes so you can plan in advance, obviously find clear skies, that's actually the hardest one, and then expansion phase, waiting for the skies to just brighten up and explode with colour. Have lots and lots of fun. Best of luck to you. Wishing you clear skies on every aurora chase that you do. If you don't follow me already, please do so on Facebook or Instagram as Will Photography. If you haven't already, please subscribe to my channel. Thank you so much for watching. Take care.